lesson for class 21. This is fatigue, but now we're going to categorize fluctuating stresses in a different way to account for the fact that we might not always be completely reversed stress. So if the stress is not completely reversed, we need to account for that. So this is section 611 and 612 and a little bit of 613. I just barely talk a little bit about that. So here is some of the big ideas right here. Right. So first we should start out maybe by drawing what the bending test is actually doing. Right. The bending test is taking a sample and it's completely reversing the stress. Right, so it goes tension, compression, and in the middle it's zero. So a time history of that, I'm looking for pens that have lead in them. A time history of that would be like this right here, right? A sine wave where here is the here is the positive stress and here's the negative stress, right? So we could call that the amplitude. Right, and we call it the sigma A, the amplitude. But what if instead we were bending it and then we were going like this right here, right? So there's always some amount of stress on it, but the amount of stress varies, right? That would be described and with this type of curve right here. And what we could do is we could now establish that we had an average, which we'll call the mean or mid-range, right? So looking at these different things, we'd have the minimum stress right here, sigma min, and we'd have the maximum. So we would have this in-between one right here that's halfway in between that we would call the mid-range, right, or the mean. Then we would also have an amplitude stress right there, right? So that would be, this would be the amplitude, and it would be both positive, both adding and subtracting from the mean. So we have a mean stress, and we have, if we add the amplitude to it, we get the max. If we subtract the amplitude to it, we get the min. They also mention some other things. They talk about the range and the static. I'm not going to bother with those. I don't even know why I include them in there, right? So it's not necessarily something we're going to talk about and think about. So this is pretty intuitive right here. We could have the stress as being max minus min and divided by 2. And by the way, we just call that whatever that is not necessarily positive or negative. Here we have the max plus the min. So this is really just the average. You got to be careful not to use the average because that A might confuse us in average, right? So and the A and the M actually can be just a little. So just the A, you could think of it as the amplitude or as the alternating. I tend to go alternating, and this could be either the mid-range or the mean. I'd usually say the mid-range. That's just I tend to use those words. We can have special case here. And this is the special case of on-off, right? So this is a bending that goes like this. Bend, off, right? Bend, off. And so we'll see here that it turns out that this is the mid-range, and this is the alternating. But this is also the alternating, right? So the alternating equals the mid-range in this one. And the minimum is obviously 0, right? So that's a special case. And of course, this is the regular thing that I drew in the very beginning. And the mid-range is equal to 0, right? So that the amplitude is equal to both the max and the min, right? The max and the min equal each other. equals to the amplitude, right? Absolute value, or I guess maybe the absolute value. Maybe I'll make the absolute value of the minimum, right? Because the minimum is going to be compressive, right? So it might never go into compression, right? Where we have, and we're talking about a particular point onto this guy right here. We recognize this point is in compression, and if we just analyze a single point, this is compression off, compression off. But here's the one we're going to care about. And something to keep in mind is that cracks propagate when they open. So it's really on the tension side that things are going to happen. If the crack never in compression, something stays completely in compression, the crack never opens. So just be mindful of that. Here's something I put in my notes. Of course, the page numbers have changed with the different editions, I changed my mind about this a long time ago. I need to get rid of this statement, but there is a discussion in the book that you shouldn't use stress concentration on the mid-range, but we're going to go ahead because the book contradicts itself later on and does use the stress concentration on the mid-range. So I'm going to try, just to be, for the sake of consistency and not to make this more confusing, just cross that out. So maybe I made it confusing by even bringing it up, but what are you going to do, right? Okay, so now we're going to try to account for this. And how are we going to account for it? Well, we are going to, okay, so here's some more discussion. And this actually brings up to the point where you can see this data over here. Here is for the mid-range, right? So, and this is a ratio, but just think of this as a mid-range, and we're going to create a graph, and we're really only going to be looking at this part of the graph over here, right? So, but bear in mind that graph, this is actually something that's been plotted, right? That you could have the amplitude, right? So in the vertical is sigma A, and in the horizontal is sigma M, the mid-range. So that's the amplitude versus the mid-range, or the alternating versus the mid-range. And these dots represent failure. And you can see how there's this cloud right here. Well, so the concept we're going to try to do here is we're going to create a new graph of alternating versus mid-range, and we're only going to look on this right-hand side of the thing. But pay attention on the left-hand side, what went on there. Notice that everything seemed to fail right here, that it didn't matter. Like it was all about the mid-range, right? It didn't really matter. Well, it was all about the alternating. Let me say about that right there. The mid-range didn't matter. So if the mid-range is compression, it doesn't affect anything. That's because that same idea that the crack doesn't open and close, right? If it's in compression. So if the mid-range remained in compression, it was only the alternating that matters. That's an interesting kind of thing. So here is a discussion. There's a lot of words, but it's worth reading through, and it's something I alluded to before, right? So I can read to you. The early viewpoint was that this diagram, this alternating and mid-range diagram thing, was like some kind of way to say this is a fence, and anything above it fails, anything below it doesn't. And that's the way we're going to be treating it. But then they found, after some research and with more data, that it was more like a zone where you could find some probability, or it was more stochastic. So we treat it like it's deterministic, right? And they're even using those words right here. It says we treat it like it's deterministic, but it's actually a stochastic phenomenon. And so you say, why do we keep doing it this way? And it's because, first off, we're going to see it's a straight line, and it makes the algebra easy. It's easier to graph, and it reveals some insight into the problem, and we can get like we can come up with an answer pretty easily. But it's also historical, right? So we say this is This is a stepping stone to understanding its history. So in order to be able to read the work of other engineers and have meaningful discussions about them, we need to know about this method, right? And so as much as these paragraph right here, or these words are telling us don't even think about it, don't even worry about it, this is the way that every engineer, mechanical engineer, gets introduced to fatigue. And when we try to work and maybe do more advanced stuff, and actually our job is to make a prediction, and we have to make a good prediction, we would use something more sophisticated this. But as a first pass and having a discussion and for design, this is the method by which we learn. Okay, so we're going to come up with these new criteria, right? So these are criteria for failure, and there's a number of them. There seems like a bunch, but don't worry, we're really only going to have a couple, right? So there's actually, it seems like a lot, but it's not that many. So the first is a Langer criterion, which turns out to not really be a fatigue criterion at all, and there's really just about static, right? So this is like a static failure. So that's what's being described, static failure. And this one becomes 45 degrees. And it's really going to be, do I write this in here? It's we can think of this as the yield line. I think of it as the 45 degree line. So on an amplitude, or alternating, I guess I went with alternating in mid-range, it's a line. Then if this should actually be scaled so that they're the same scale, but here this should be like 45 degrees, and we say that we're right in there. And the idea is of this graph, by the way, is if you plot like the stress, the mid-range stress, and you plot the alternating stress, and you find a point right here, this is like a load line. And if you continued along with that same ratio, right here is where it would cross, right? So here is the actual point, and here's where it crosses. So what we're essentially going to say, and what we have down here as an equation for this, I've changed my notes. So if we want to have a safety factor, oh no, I'm sorry, I got to go down to my static yield right here. We say that the safety factor for Langer is going to be equal to the yield strength divided by the alternating plus the mid-range. And that actually just kind of makes sense, right? Because isn't the alternating plus the mid-range, right? Here you go, right there. Here's your mid-range, and here's your alternating, right? Isn't that just the maximum? Aren't you just taking, alternating plus mid-range is the maximum. So this is just a static stress, right? If it exceeds, if it exceeds the yield strength, it has failed according to, or it has permanent deformation, right? So on this graph, what we're representing right here is, this is the safety factor, right? If it hits this point right here, that sets it equal to 1. All right, it has a safety factor of 1. If it's greater than this, it has a safety factor of less than 1. If it's below here, it's a safety factor that is greater than 1. So we have a margin right there, and that represents the physical margin. So you remember how we did the failure loci, right? This is the same kind of concept, right? This is how far underneath this line we are safe from yielding. How safe are we? It's the ratio right here. And that's the same thing for the rest of these. They have different values that we use in the y and the x, and some of them have like a curvature to them. So the first one we do is a Soderberg right here, and this is the most conservative of these criteria, conservative, and we can think of this as, I'm going to call it SE to yield line. This is the SE to yield. So we get the endurance strength, which is obviously less than the the endurance strength right there, and we go to the yield strength right here. Boom. And we can see that our point right here is outside. So does it fail? Well, it fails to be infinite. All right, so outside of this line means that you will eventually fail. Right? That doesn't mean that you're totally and completely, immediately. It doesn't mean you immediately fail. It means that eventually you will fail. Right here. So right here you'll see this is where you're predicting infinite life. Anything below here will definitely be infinite life. Above it, it will eventually fail, and then you can kind of we will see soon how we're going to predict what that life is going to be. All right, let's get that back on there. And for an equation for this, this is equation 645. I'm going to write it the same way that they write it, I think, where we're going to take sigma A and divide it by our endurance strength. This is an apples to apples thing, right? This is an alternating stress. This is an alternating strength. Plus mid-range. This is a statics. This is a constant stress divided by yield, which makes sense, right? And that's going to be equal to 1 over, and I like to go solder right here. The next one to do is called modified Goodman. I'll explain what the modified mean, but we just usually just call it Goodman. And this is the most common, and the one that I will basically use almost exclusively, right? And this is now, you can think of this as being an SE to ultimate. And it kind of makes more sense than the Soderberg, because failure on the mid-range is due to it being bent and it not going back in its shape. Failure over here on the alternating means it breaks apart into things. So it makes a little bit more sense to have these two things tied to each other, right? And so, and we should label this right here. Here's the Langer to keep track of it. And sometimes I'll like make it different, like line type right here. But here's the Goodman. And maybe in here I'll write the Soderberg. Label it right in there. And the modified part of it is kind of like we want to follow the line until it gets to right here. And if it ends up in this zone, well, it's gonna yield, so that's still bad. So maybe that's the modified part of the Goodman, is to keep like a little knee right in there. So it's like an extra little check. But basically, most of the time, we're gonna go with just taking this. And as an equation, you can almost predict this yourself. Well, of course, we're taking a ratio of the alternating to endurance still. But now in this one, instead of using yield, we use ultimate. And so that's 1 over n, and I go good. Right in there. That's the Goodman safety factor. The other two are really just modifications of the Soderberg and the Goodman to try to account for really this thing right here, right? So this is that same. Remember, this is mid-range right here, and the vertical is alternating. So and this is the ultimate strength. No, this is the endurance strength right here, and this is the ultimate strength right here. So that line you're seeing, this is the Goodman one, right? The if I was going to change colors, and it lets me, let's see if it lets me change colors. I'm gonna go green. This would be like maybe the Soderberg. No, the Soderberg would be like down over here. Yes, because yield would be maybe, let's say the yield is 80% right here. So here's our Soderberg. Boom, right in there. But notice that there's sort of like, I'm going to say an arc kind of to the data, right? Somebody went like, oh, wait a minute. There's a little bit more like a kind of thing through the data, right? Or, and then maybe somebody else said, well, you know, it's actually more kind of like this right there, right? So that's what these next ones are going to be, right? So we have this Gerber. This is similar to Goodman. Let's see if I get this one. Let me see if I got that right. Similar to Goodman, but curved. So it goes from Goodman and goes wee, boom, like that right there. And its equation has a little bit more complexity to it. So it says that we have alternating to endurance, but now the here's there's a safety factor is right in there. So maybe I need, if I'm going to be consistent, let me see if I can be consistent. Let's write N-Gerb times the alternating plus N-Gerb times the mid-range over the ultimate squared equals to 1. And then you would need to use algebra to get the Gerber out. But don't worry, they've already done that for you. I'll show you where that is in the book. And then the last one is the ASME-Elliptic, and that's really just similar to Soderberg, but curved. And so that one's going to be like this line right here. I didn't have a line. This one's Gerber. But the ASME-Elliptic is something like that right there, right? So, and so I guess I'll try to label him too to be consistent. This one's a little more, even more obnoxious. So we have the safety factor, ASME, we'll call it, and the alternating divided by the endurance, and that's squared. And then this one is we also do the ASME, and now the mid-range and the yield strength squared equals 1, right? But they're all the kind of the same. They're the same. But the Goodman is the main. The Goodman is the good man. He's the one that I'm going to go with for most of our calculations. Why? Because once again, they're all not great. But Goodman's the easiest to use, makes about the most amount of sense, and as far as I have seen, is the most common one when these discussions come up. So I think I have some more interesting slides to show about this. Boom. Remember what a safety factor, these are all safety factors we're going to try to find, but remember that the safety factor means that we are above the endurance strength, so that we're somewhere over here, right? And therefore we're going to fail eventually, and we predict failure. So here's just, I made these, so I just kept them, right? So here's the Langer right there, right? So out of this line. And here is how they write out the safety factor in the book. I like the way I wrote mine better. But there you go. Here is the modified Goodman, right? And you can see that's how it's modified, right? Inside the blue zone, safe. Outside the blue zone, not safe. And there's the Soderberg, and you can see it's a little more conservative because it kind of cuts off right there. So there's your Soderberg. And there's the Gerber, right there. So you can see the Gerber is connected at the same point as the Goodman over here in the Ultimate. And then here is the Soderberg, which is, the ASME-Elliptic, which is right there. And here are the equations. But let me go to the book, which disappeared on me. No, here it is. Let me take a look in the book and show you that if you wanted to get the safety factor things, it's kind of, let me see if they fixed it in the 11th edition, because it's always been just a little bit weird how they organized these. They might have added some good content in there. They added some good content. Oh, I like that. I don't think some of these curves were in the previous editions. They look new to me. So there is some of those descriptions right in there, and some of that cloud of data, and you can get that kind of idea. They do have a whole bunch of other kinds of curves and things that you might want to read about, but I'm not covering. Here is that same diagram that I just showed and went one step at a time on. I'm not familiar actually with this guy right here, so I might have to read up a little bit more, or this those two things. So I need to read up on that. That's new. I like that. Good. Way to go, Shigley, improving stuff. In fact, actually, it's interesting. They're leaving out what they used to do. Okay, so in the older version, they had, you've had the 10th edition and earlier, you will find that you have some tables that give you the equations to solve for the stress concentration right here. I mean, not stress concentration, for the safety factor. I just disappeared for a second. How did I disappear? I don't know. So anyway, Morrow. I'm trying to find these other guys right here. I don't want Morrow. It's identical to the Goodman line. All right, so let me see here. I will learn about that later. Okay, so here start with Goodman, and here's the safety factor, and I put subscript G good underneath there, right? And remember, this is when the mid-range is greater than 0, right? So if it has compressive mid-range, we have to do something about that. Gerber. This is solving. It's a lot uglier, right? Because the Goodman had the Gerber had the safety factor stuck inside the parentheses, right? It was in here, in there, and there. So they had to do some math. So they have done that for you right here. So you want to evaluate the Soderberg. Right here, so here is the safety factor, and then the ASME-Elliptic, also because of the that wasn't as difficult to get the safety factor out of the thing, so it's not as much. And I don't know what the Smith-Watson topper is. I haven't read that part of this chapter. I haven't had the book that long. So anyway, if you get the other editions of the book. Just going to tell you where those things are. Let me go grab my an older edition here. So let me pause. 10th edition, and the organization of this is a little weird. So this is the Goodman one, where they give you the Goodman. There's a bunch of other things about intersecting coordinates and so forth, but this is the equation that was really useful to us in this. And then in table 6-7. Here's where they solved the Gerber safety factor, and that's really the one that we care about. The rest of this stuff is about doing some graphing things. And then lastly, here is the ASME-Elliptic safety factor right there. So just giving you an idea if you're using an older version of the book, where you might look for this. And okay, so I think I'll keep continuing on, even though this is probably a longer video than you would want. We have one last thing that we are going to want to describe, right? And that is how do we use this in order to predict life? Okay, so the idea is so the modified Goodman here, based on this graph that I have right here, is this line right here. So I'm going to highlight this. So I'm going to use the modified Goodman. So first I'll evaluate the safety factor. Is it above 1 or is it less than 1, right? What does it mean? It means that it's not infinite. I said that wrong. If the safety factor is less than 1, it's not infinite, aka finite, right? So it will eventually fail. So we want to figure out how do we go back to that SN diagram and figure that out, right? The SN diagram looks like this right here, right? It's got that. Here's the 1,000 and here's 1 million. So we're above the endurance strength. Well, what we need to do is we need to convert our sigma A and sigma M, convert it into an equivalent completely reversed. And in some of the books, I'm not sure, I kind of noticed that I didn't see this exactly written out this way in one of the spots that I thought it would be in the 11th edition. So it might look a little bit, but we have sigma rev. This is the equivalent completely reversed stressed, right? And the way we find it, okay, so let's say that we're outside this Goodman line. We're going to be like right here. All right, so we have, say I picked a mid-range of 30 KSI, and here it looks like I have, let's just say I have 15, but it's of amplitude of, alternating of 15. Right. What I do now is graphically, I'm going to start at my ultimate strength and go through here, and I'm going to find this guy right here, and I'm going to call him my sigma rev, the equivalent completely reversed. I've kind of like modified this and zipped up and went through there. That's what I do graphically to do this by way of an equation, and this is based on Goodman. I'm going to say we're based on Goodman. We have the other ones that we could have done it to, but we have this based on Goodman. We take it ends up being, because of this idea right there, we have sigma A divided by 1 minus sigma M divided by the ultimate strength. And in the 10th edition, this could only be found in an example. So I want to see, did they ever do this? That was example 612 in the old book. Now, what are we doing in the new book? I do not know. We have constant life curves. Okay, so they have a new section, I believe. I believe there's a new section in the 11th edition called Constant Life Curves. And I see under the Goodman, very inaccurate for purposes of estimating an equivalent completely reversed. Its inaccuracy is almost always in the very conservative sense. But here is the equation that I just wrote right here. So this equation used to only be, if you have the 10th edition, in example 612, but now it's right here. And there's also a Gerber one that they do, right? There was also a Gerber one, and I don't see it in here, But that's another means of them trying to, they had a version of it to try to predict life. And I need to reread through this latest edition right in here. But if you had to, so this was like the Goodman version. And they had the Gerber version of this sigma rev, and that was the alternating stress divided by 1 over the sigma m over the ultimate right here squared. I just went ahead and stuck with this equation right here. So this is what we do if we have a stress if we predict if we have a safety factor that's less than 1, we're going to go it's going to die. Well, then how do we figure out when it's going to die? We get this completely reverse stress, which is equivalent to doing this thing right here, right? And then we come into here and we say, here's our sigma rev, completely reverse, and there, right there, that's our prediction for life. And as the book says, it's not a very good prediction, but it's conservative, so worth covering. So I think the next is going to be an example. So there you go. Alternating and mid-range combined together in order to evaluate. So we're getting closer and closer to apples and apples, right? Where we have a pure bending data that's going on here, and we're trying to convert it into we're trying to convert our stress state into something that's comparable, so that we can go to this SN diagram and predict the life.